we are presenting a talk on deep learning and machine learning security. So the title of our talk is GDALR, an efficient model duplication attack on black box machine learning models. So this is a little bit about me and Revant. I am a security researcher at Prior to Software Labs, and Revant is a security consultant there. So I basically work on applying machine learning and deep learning in different security domains, and also on the security of machine learning and deep learning systems. So it goes kind of hand in hand. Revant is an open source developer, and he also does the VAPT and pen testing things. So, and this is a little bit about our company, Prior to. We excel in IoT, cloud, and mobile testing, and we have in-house fuzzing infrastructure, and we have just started deep learning and machine learning specific pen testing. So this is the agenda of our talk. First, we'll go through an end-to-end pipeline of deep learning. How many of you have previously used deep learning in your projects? Yeah, few of them. So yeah, what we can do is we can first try to understand how deep learning is implemented in some projects, so that it will be easier for us to understand what are attack vectors and how the attack can happen on deep learning models. Then we will dig deeper into model stealing attacks, the topic of our talk. Then we'll see the previous implementations of model stealing attack, how people used to implement, how people used to steal models from deployed applications. And then we'll see the attack methodology that we have developed to steal the models. So, sorry for the formatting there. I've developed the slides in Google Slides, and then it is converted to PPTX, and it's been presented in PowerPoint. So there could be these formatting issues there. So sorry for that. This is a basic building block of deep learning, which is called perceptron. It is inspired from the neuron in our brain. So the way we process information and make decisions is mathematically represented, and if something is mathematically represented, we can implement it in computers and simulate the functionality of our brain in computers. So this is a basic building block of what we call a neural network in deep learning. So here you can see that there are X1, X2, and X3 inputs that are going in. Okay. So these X1, X2, and X3 are the inputs that are coming from our feature space, and it is passed to a neuron, and then it processes or triggers, you can say, and we get some output. So these X1, X2, X3 could be image pixels or any other features. So if you have data coming in from multiple sensors and you have to make decisions based on the data, so those X's could be the data from your sensors. So this is just a single neuron, and if we connect these neurons in multiple layers, it is called a neural network. So the inputs are coming there, the X1, X2, X3, and X4 are the inputs, and then there is a hidden layer. We can have multiple hidden layers as much as we want, and there is one output layer. So based on number of classifications we have to make, the neurons in output layers is decided. So yeah, now we have X1, X2, X3s are as inputs, and there are some weights which are multiplied by inputs, and we get the activation from that neuron. So here the weights are the values that actually determine how the input is interpreted by our neural network. So you can see every node is connected with some weights, and those weights are initially randomly initialized. So the example here is you're passing image 3 to a neural network, and we want that neural network to identify the image as 3. So the image is 28 by 28, has a pixel size of 28 by 28. That means it is 784. There are 784 pixel values that are being passed. And in the first layer, there are 784 neurons. So it will take the input values, which are pixel data, and then it is passed to different layers, and at the output layer, we get some activation. So this activation is supposed to be, like this one. So if we are passing the input as 3, we want third neuron to be activated. So this is how we want the neural network to work. But we are getting some random output because the weights are initially randomly initialized. So now our task here is to change the weights in such a way that when an image is passed, it will trigger that specific neuron in output layer. So this is how the training works in neural networks. We pass the input image, we get the output, we try to compare the output that we are getting from neural network and the output that we actually want. The comparison between these two outputs is called cost in machine learning terminology. So our aim is to determine the weights in such a way that the cost is reduced, which means it will trigger the respective neuron in the output layer. So you can see the 4 is passed and we are getting some output, and then the algorithm is changing the weights. So we will dig deeper into this algorithm. Here's an analogy to make. If we have a dartboard and you are throwing some dart at the dartboard, so how will you actually learn to hit the bullseye? We first throw a dart. Suppose we hit the point P1 here. So after that, in your brain, inside subconsciously, what you think is you have to move your hand towards the bullseye so that next time you hit the bullseye. So what mathematically you are doing is you are moving your hand directly proportional to the distance between P1 and the bullseye. So if the distance is more, you move your hand more. If the distance is less, you move the hand less. So this is a representation of gradient in machine learning. So that difference is actually called gradient. And based on that gradient, you actually change the weights and you get the desired output. So it will be moved more and you will hit some other location. So that learning methodology is implemented or represented in this way. So we have some initial weights. Then here alpha is called the learning rate, which determines how magnified or how abruptly you change the weights of your neural network. And this C is the cost function, which is the output that we are getting, the difference between output that we are getting versus the output that we actually want. Okay, so after going through this equation multiple times, n number of times for n epochs, you get the weights that actually predict the output that you want. So if you pass the image of 2, it will activate the second neuron in output layer. So that means your neural network is working and you are getting the output from your images. So the previous one is called multi-layer perceptron. Now there is another type of neural network that is called convolutional neural network. So multi-layer perceptrons are used where you have vectors of data, and convolutional neural networks are used where you have images as data. So it kind of doesn't make sense to pass an image to multi-layer perceptron because some pixels in an image actually don't represent anything about that image. So if you are writing 3 in an image, the background, black background will actually does not represent anything. So if you are passing those pixels to your neural network, it might just confuse the neural network, or it will take more time to train the neural network. So that's why convolutional neural networks are designed. So there is a concept of filters. So this is the image with some pixel values. There is some filter which is multiplied with the image, and that filter is passed over the image with some distance. So you multiply each value of this filter with every respective value of this image, and then you get the first value. Then you move the filter to right, and then do the same operation, then you get the next value. So intuitively what it does is it actually captures the features inside an image. So let's say you have to differentiate between a table and chair. So this filter will actually learn to identify the curves that are in the chair, and the neural network will try to differentiate the curves with the straight edges that are in the table. So that is the use of this filter. So this is an animation of how the filter passes over and how we get the data. So the animations that I have previously used was taken from 3 Blue 1 Brown's video. It's a great mathematician who does YouTube's videos, and I suggest you to go and check his videos because it will give you a great intuition behind mathematics, and you might start liking it. So after convolution, the result of convolution is again passed to normal neural network that we have previously seen, and in the same way the weights are adjusted and you get the classification that you want. Okay, so enough of mathematics. Now a trained neural network or a trained model, what it means is you are just saving the weights of that model. So to train a model, you actually need to invest a lot of resources. So it's like few terabytes of resources, and few weeks of time is invested in training those models. So whenever a company prepares a model or uses deep learning to build their products, so they are investing a lot of resources, and if some attacker gets access to those models, then that attacker might not have to pay the owner of that model, and it's a business loss for that company. So in model stealing attacks, there are two types of attacks, like you can see, offline and online attacks. So these models are either deployed on device with the executable package, or these are deployed on cloud, where you can query the cloud and get the results. So for example, an image detection model will be deployed to cloud, and then you pass your image to cloud, and then it will tell you what object is there in the image. Or in case of firewalls, let's say someone uses firewalls to detect malicious queries with non-malicious queries, then you have the model. You need the model to work offline on your system. You don't want every query to be sent to the cloud and get the detection from there. So in that case, the models are deployed offline. So attacker can actually do the offline model stealing attacks, which we will see, and the ones that are deployed on cloud can be stolen by online model stealing attacks. So these are some vague steps to steal the models using offline model stealing attack. First, you get the executable, you reverse engineer it, try to find where the model is stored on your device, and then try to understand how that model is built. So there are multiple frameworks like TensorFlow, Torch, Keras are being used to develop these models. So once you get to know how the model was developed, you will use same APIs to use same frameworks to get access to that model, and yeah, you have the access to model. So here's one use case that we have tested, an application that we have tested against model stealing attack in our company. So this application is an Android application that does image detection. It will detect objects in an image, and they ask the user to pay to use different kinds of models. So there are models to detect types of dogs and species of cats. So if you want to use those specific models, then you have to pay the vendor to use those models. But when you reverse engineer it, you just dig into the code. I've used JADX to get the Java from APK. So you can see that there is some categories file. So this categories file will map the output of your neural network with actual category. So let's say a 530th neuron is activated. That means the input image belongs to some other category. And the model is stored at this location, and the input to the model is of this size. So now you know all the details that you want to access the model. So after going to that location and checking the hex dump of that model, I can see that there is something called nn.sequential torch.float tensor, which actually tells you that the model was developed using torch framework. So now your task is to go and read about torch framework and try to understand how you can load that model using torch. So I did the same thing, and I came to know that there is load Lua function which can take the model, and you can have a subroutine predict, and it will try to predict the image. So I've used it and I got the error. So after digging into the error, you can see that some layer is expecting the input to be of dimension 2, and the layer is called legacy/nn/linear.pyc. So later I've loaded the model and saw what layers are there in the model, and I could see that there was some layer called view layer, which was accepting so this view layer, which was giving out the result of 128 sized vector, but the linear layer is accepting the input of size 2. So I've just changed the output from view to 1 by 128, which does not actually change the values in the vector, it only changes the shape of vector. So yeah, once that's done, we got the access to model, and we can load any model that we want, and we don't have to pay the vendor of the application. So this was all about model stealing attacks, offline model stealing attacks. Now, what if you don't have access to the code and access to the models that you want to steal? So the models are, suppose the models are deployed on cloud, the application is there on cloud, you just have the API access to those machine learning models. So Revant will give you a brief introduction about how those models are deployed on cloud and how the access is provided and what kind of output you get from those models. And then we will see how we developed an algorithm to attack those models.
Thanks, Nikhil. So we'll be focusing on online machine learning models. So I'll be introducing you to machine learning as a service. As Nikhil explained till now, offline models are very easy to retrack. Anyone can try to deploy it in their own business models and they can sell it. So people started moving themselves into online machine learning models. For example, these are the vendors which host their models on the cloud APIs, cloud servers, and they provide the APIs to use these services. And they do charge the users per query. So if the user is making 10 requests, then they have to pay the money for those 10 queries. So these are multiple vendors like Amazon, Google, BigML, Microsoft, and so on. So this is an image from the Microsoft's machine learning approach, how they serve the online machine learning models. Yeah, you can see pretty much there's the cloud server, and the user will be able to make the request through an API. And once the request is processed, he'll get back the results and he can do the predictions locally, and he can do it on his simple UI. So this is how the machine learning as a service works. The models are deployed on the cloud, user will send his input, the data is processed on the cloud, and you'll get the output labels. So even these models can be stolen and they can be replicated locally, which will eventually lead to some loss to the companies because they won't be earning their revenue. So the first attack methodology was proposed by Tremer in 2016, where he is able to send some queries to the model, he's getting the output, and then he's using the output to train his model locally on his system. So once he trains his model with so many requests, it will become almost equal to the model on the cloud, and then the user can use the local model to make the predictions, and he can even sell it on the black market for lesser price. So people will not use the models which are on the cloud, and that will lead to loss to the company. This is a simple, I'll try to simplify this, and something like that. This would be simpler than the previous image. So simply the trained model is deployed on your cloud. There are these APIs. So a user will simply send his input, it's processed, and he'll get the target label. So how can the attack happen? Something like this. So the part on the right side is the first step. So the user will be sending the input. He will take the target class, and then he will use that to train his model F dash on his cloud. So once he's training the model on F dash, there's no need for the user to pay the money because it's on his cloud. And yeah, it is something like this. The input will be an array of features. So here's the main difference between the actual output and the output generated by the cloud. When you're trying to predict the class of an input, the cloud API just returns you the maximum value of the output. Let's say there are 3 classes and the probability values are 0.1, 0.2, and 0.5. So it's technically saying that the particular input belongs to class 3. So as mentioned here, the cloud API output returns the maximum of the probabilities. But in actual, there are 3 different classes and their probabilities vary from each other. And these are very important to train your models. And we'll see how it is. Yeah. So this is the present attack methodology where your cloud API output will be binary values. Either it will be 0 or 1, and you'll be using that to make the predictions. And attacker will be using these values to train his models locally on the cloud. But the issue with this is, as I mentioned before, let's say this is your input 1, 2, 3, 4, and the actual output is some probability values. So the model predicts there is 0.3% chance that the particular input belongs to class 1, 0.2 probability that the particular input belongs to class 2, and so on. So the cloud API just takes the maximum of that and it returns 001, predicting that it belongs to class 3. So the traditional assumption made by attackers is 001 is equal to probability values. So this is actually not true, but the current approaches focus on this thing and they use 001 to train their models, which will eventually take them longer hours, more number of queries to increase the efficiency of their cloned model. So we propose some approach in which we will try to fix this issue. Yeah, so this is just a graphical view of the probability losses. As I mentioned, the cloud API output is just the binary values and the actual output value is the probability values. So when the attacker is assuming the output to be 001 or 010, then he's having an unconventional probability loss. He's losing this much values and it will take him more time to clone the model. Yeah, so that was the issue. So we found we just try to reconsider the way to attack these models. So the first one comes here, sorry. Yeah. So first thing is we consider the way we analyze the labels. Instead of taking the labels as 001, we try to take the probability values into consideration. And the second approach is we try to learn the parameters in hyperspace. You can read the first point. It says we need to learn the boundaries of the target model. What that means is you have to make sure your model predicts the output in such a way that it is equal to the actual cloud output probabilities. And the following points are also something similar. It just says you should not consider the class to be the binary values. We should consider the gradient loss as well. And yeah, the last equation represents you the traditional equation, how the attackers are using the methods to steal the models. So they just try to optimize the cost, keeping the learning rate constant. Alpha is the learning rate here. So we tried to propose a new method in which we will try to change this equation to optimize the problem. So Nikhil will continue with the proposed approach.
Okay. Just to summarize what Revant just said, we can take an use case of image prediction. So the attacker is trying to predict, attacker is trying to attack the image prediction model and trying to steal that model. So attacker has a set of images that he wants to predict and doesn't want to pay the cloud provider. And the cloud provider has deployed his model on the cloud, and it's predicting the images quite well. So what attacker can do is he can take a subset or entire set of his images and provide it to the cloud provider initially and get the labels from cloud provider and use those labels to train his own model, and then use his own trained model to do the further predictions on his images. So to do the further predictions, previously attacker has to pay the cloud provider because he has to send the images to cloud provider. But now that he has his own model, he doesn't have to pay the cloud provider. So as we can see that there is some unconventional probability loss which contributes to increase in cost. So if the cost is increased, it will directly increase the weights. So our model, our F dash, will not be trained that efficiently. In that case, what we can do is the W is fixed. We cannot do anything about W, the weights. The cost is fixed in a manner that we are getting an output from cloud API. We don't know the actual probabilities that the model on cloud is predicting. So now we have only alpha to change, which is the learning rate. So what we propose is to change learning rate based on gradients. So if the gradients are higher, that means there is something fishy in the outputs. So we change the learning rate to a lower value. So after the multiplication, this value will be lower and weights will not be changed with higher magnitude. So we change the learning rate based on cost function. And this is how the mathematics looks behind our proposed algorithm. So the fact I is the factor that we are multiplying the learning rate with, which actually takes the G dash, which comes from the G. So you can see as the gradient increases, the learning rate will automatically decrease on this slide. So here's a small animation. You can see that the gradient is increasing. So G dash is actually gradient passed to tan H. So gradient is increasing and the fact I is decreasing, which is the factor. So this factor will be multiplied with your cost. Then the weights are changing that way. Yeah. So to test our algorithm against the traditional attack methodology, we have used different classifiers, different methods of classification, and on different data sets to check whether our algorithms works better or not. So there are three main classifiers that we have used. First is logistic regression, which is kind of does the same task as what neural networks do, but I don't think it's good to bash your heads with mathematics and get deeper into the mathematics, which is not required for this presentation. Second is multi-layer perceptron, that is what we have seen previously, and the convolutional neural networks. So these are our results with logistic regression. We have trained the logistic regression with one standard iris data set. So there is a data set of iris flowers. which has sepal width, sepal length, and petal width and petal length, the 4 features of flower, and it will predict what species the flower belongs to. So first we have trained the model using the data set. Then we used our methodology to attack that model and duplicate that model. And we have used previous methodology to duplicate the same model. So here you can see the yellow or orange line represents the previous methodology, and the green line represents our methodology. The aim of optimization is to minimize the loss. So whatever methodology is giving you minimum loss can be called a better one. So with different learning rates, you can see the loss is increasing in previous method, previous model stealing method. But our model stealing method tries to over-counter the cost that you are getting and stays with the same loss. So T loss is the traditional methodology loss, and P loss is the proposed one. So you can see the difference here. It's around 4 times better than the traditional method. So similarly in multi-layer perceptron, these are the learning rates that we have considered for prediction. So if you want to know more about these experimentations, we have also published this in IEEE. It will be live on IEEE Explorer after a while. So here you can see that after around 10 epochs, our algorithm already found the best loss. And in this graph, you can clearly see that there is significant difference in the traditional and proposed methodology. So with convolutional neural networks, we have trained this on Landsat dataset. So the dataset has images captured by satellites, and we have to classify, the model has to classify the images which represent different terrains of land. So there are multiple terrains, and there are multiple classes. So this is not just a binary classification, there are many classes. So the number of classes increases will actually contribute in the traditional unconventional probability loss. So more the number of classes, more better the GDALR will work. Yeah, so conclusions and mitigations. You can clearly see that the proposed method works quite better with to steal the models, the online models, and people are trying to research about the mitigations that you can implement to stop attacker from actually stealing those models. So some are proposing to change the probability values that you are sending to the user that is using APIs. Some are saying that you can use machine learning to detect the attack that is being used by the attacker, attack methodology that is being used by the attacker. But there are no reliable mitigations as of now. So this actually opens a wide area in machine learning security itself to research more on how to stop these kind of attacks and how to make machine learning as security better. Yeah, this is all about us. You can, if you have any questions, you can tell me. Yeah.
How much queries do you need in order to duplicate model and have disintegrers?
Okay, so that depends on your target model. So if there are multiple classes and there is much segregation between in the hyperspace, you do the machine learning, so I can use those terms, right? In hyperspace, there is much segregation between the classes, then you actually don't need more number of queries to attack the model. But yeah, if there are, like, the data set is complex, then obviously you have to use more queries. Does that answer your question? Yeah. I think you have...
Oh, the same question.
Возьмите микрофон. Okay. Yeah, thank you. The same question about the amount of queries do you need to duplicate the model to achieve the same accuracy as the base one, or precision, recall, whatever?
Yeah, so if you talk about accuracy, it doesn't matter from attacker's perspective. So if you talk about image detection models, So on ImageNet dataset, there are models that have been developed which classify images into 1,000 types of classes. But attacker might not want to classify 1,000 types of objects, right? He might be having only 5 kinds of objects in his work domain. So you just have to learn 5 types of objects and not the 1,000. So it depends on the dataset or the classification task attacker wants to do. You don't actually have to have the accuracy similar to the one that is deployed on cloud. You just want to complete your own task. That's it.
And I suppose there are a lot of API limits on that side. I mean, that original model has.
Yeah. So in that case, there is no option other than paying the cloud provider. But again, once the attacker does some initial investment, he has the model. That's it.
Thank you.
Yeah, any more questions? Yeah.
Thank you. Thank you for your talk. What the limits of the complexity of model sorry. I use my translator, okay? It's hard to
no problem.
keep my mind on. Okay. Second. What is the limit of the complexity of the model so that it can be copied for an adequate time, for normal time?
Yeah, so this is like another version of the
sorry,
same question.
I just walk out.
So based on the dataset that you have, the dataset attacker has, he has to think about the complexity from attacker's dataset, not from the perspective that the dataset that is being used to train the model which is deployed on cloud. So the service providers will have to think about multiple cases. So attacker might not have that many cases. Attacker might have some another classification problem with a limited set of classes. So in that case, it will be easier. Or if he has more classes, it's difficult.
Okay. But if we have some... it's too hard. But if we have some limits on the server side for requests, then we can ask for server.
So on server side, they cannot totally restrict you from accessing the models because that is their business perspective. They want users to access the model.
Sorry, the question is not about it. The question is about is it may make more safety for service if we limit the request?
Yeah. So as a developer of model, you can limit the queries, but that will cause the user experience, right? So what if an user wants to query your model 1,000,000 times and wants to pay you for the 1,000,000 queries? Yes. So in that case, it will interfere with the usability.
Yes. Okay, thank you. Thank you.
Thank you. Yeah, thank you everyone.